Right now, at this exact moment, the most powerful telescope humanity has ever built is staring into a region of sky that should contain nothing unusual, and the data coming back does not match the predictions, not by a small margin, not by the kind of comfortable discrepancy that a graduate student fixes with a footnote. The James Webb Space Telescope is returning images of galaxies that should not exist yet, measurements that contradict each other by 5 standard deviations, and structures so mature they look like they had billions of years to form in a universe that was only a few hundred million years old at the time. The standard cosmological model, the single most tested framework in the history of science, is being stress-tested from multiple directions at once, and some of the cracks are pointing toward an idea that most physicists spent decades refusing to take seriously, that our universe may not be the only one. That something beyond the edge of everything we can observe may be pressing inward, bending light, warping structure, and leaving fingerprints on reality that we are only now precise enough to detect. We are going to walk through those cracks one at a time. We are going to look at the data that does not fit, the cold spot that has haunted cosmology for 20 years, and the theoretical door inside Einstein's own equations that nobody ever wanted to open. Stay with me because this is where the map of everything starts to come apart at the edges. Subscribe now if you want more stories like this because we are just getting started. Let's go back to where this story actually begins. On December 25th, 2021, Ariane 5 rocket lifted off from French Guiana carrying a folded telescope that had taken over 20 years and $10 billion to build. The James Webb Space Telescope was designed with a specific purpose: to see the infrared light that Hubble could not. The oldest photons in the universe, the ones that have been traveling for over 13 billion years, have had their wavelengths stretched so far by the expansion of space that they have slid out of the visible spectrum entirely. They are not faint. They are invisible to optical telescopes. Webb was built to catch exactly those photons. Its primary mirror stretches 6.5 meters across, nearly 3 times the diameter of Hubble's, assembled from 18 hexagonal beryllium segments coated in a layer of gold thinner than a human hair. Behind the mirror sits a sun shield the size of a tennis court, 5 layers of material that keep the telescope cooled to roughly minus 233 degrees Celsius. At that temperature, Webb's infrared detectors can pick up the thermal signature of a bumblebee at the distance of the moon. Webb traveled to a point called L2, a gravitational balance point roughly 1.5 million kilometers from Earth, where it sits in the shadow of its own sun shield, almost perfectly still, staring into the deep past. The first full-color images arrived in July 2022. They were sharper, deeper, and richer than anything the astronomical community had expected. Within weeks, the surprises started. Within months, they became a problem. For decades, the Lambda cold dark matter model described the structure and history of the cosmos with extraordinary precision. Lambda stands for the cosmological constant, Einstein's term for the energy embedded in empty space. Cold dark matter is the invisible scaffolding that holds galaxies together, matter that interacts with gravity but not with light. Together, those two ingredients build a picture of a universe that began roughly 13.8 billion years ago in a single hot point, expanded outward, cooled, formed hydrogen, formed stars, formed galaxies, and has been stretching ever since. This model works. It predicted the temperature pattern in the cosmic microwave background, the faint afterglow of the Big Bang, years before instruments were precise enough to confirm it. It predicted how galaxy clusters would distribute themselves across the sky. It predicted the ratio of hydrogen to helium forged in the first few minutes of creation. Every major observation for decades reinforced it. Lambda-CDM was not just a good model, it was the model, the foundation everything else was built on. Then Webb started delivering data, and the foundation developed fractures that ran deeper than anyone had prepared for. Webb's observations of early galaxies revealed structures that were too large, too organized, and too mature for the age the model assigned to them. Galaxies that should have been raw, chaotic clumps of newly forming stars were instead presenting fully developed disks, spiral arms, and active star-forming regions that the model said should have taken billions of additional years to assemble. A study led by researchers using the JADES survey found galaxies with stellar populations so old they approached the age of the universe itself at that redshift. One galaxy, cataloged as JADES-1050323 at redshift 6.9, showed a stellar age that appears incompatible with being younger than the universe at that epoch, at a statistical significance of 4.7 sigma. If confirmed, it would directly contradict the Lambda-CDM timeline. The model said these galaxies could not be there yet. They were there. But here's the part of this that stops being abstract and starts being personal. Lambda-CDM is not just a theory about distant galaxies, it is the framework we use to understand the age of our own solar system, the rate at which the space between galaxies is stretching, and the long-term fate of everything we will ever see. If the model is incomplete, if something fundamental is missing from it, then our understanding of how our own corner of the universe fits into the larger picture shifts with it. We do not yet know exactly what these cracks mean for the big picture, but the fact that we now need to ask the question at all, the fact that the most precisely tested model in cosmology is showing stress fractures from multiple independent directions, is itself a moment worth paying attention to. And Webb's early galaxy problem was not even the most uncomfortable crack. There was already another one, older and more stubborn, that had been growing for over a decade. It is called the Hubble tension, and it refuses to go away. The Hubble constant is the number that tells you how fast the universe is currently expanding. There are two main ways to measure it. The first looks backward using the cosmic microwave background to calculate how fast space was expanding in the earliest moments and then projecting that forward. The Planck satellite, which mapped the CMB with extraordinary precision, gives an expansion rate of roughly 67.4 kilometers per second per megaparsec. The second method looks outward using nearby galaxies and a class of pulsating stars called Cepheid variables to measure how fast galaxies are actually receding from us right now. The SHOES team, led by Nobel laureate Adam Rees, gets roughly 73 kilometers per second per megaparsec. Those two numbers should agree. They do not. A gap of roughly 6 units might sound small. In cosmological terms, it is a chasm. Imagine building a bridge from both sides of a river using the same blueprint, only to find that when the two halves meet in the middle, they are off by a full foot. The engineering was careful. The measurements were precise. Something in the original blueprint was wrong from the start. Multiple independent teams using multiple independent methods keep arriving at the same disagreement. Webb itself has been used to verify the local Cepheid measurements, confirming at better than 8 sigma confidence that crowding effects in Hubble's data were not responsible for the discrepancy. The Hubble tension has now crossed 5 sigma, the gold standard threshold in physics. That means the probability of this disagreement being a coincidence is roughly 1 in 3.5 million. The Hubble tension is not a measurement error. It is a property of the universe, and nothing inside the standard model produces it. If you are the kind of person who finds this as strange and fascinating as I did while researching it, go ahead and drop a like on this video right now because it genuinely helps this kind of content reach more people who would enjoy it. Now here is where the story takes a turn that most cosmology videos do not follow, because most cosmology videos stop at the tension and say, scientists are working on it. I want to go further. Because while the Hubble tension was growing, and while Webb was finding impossible galaxies, there was a third anomaly sitting quietly in the data, older than either of them, that nobody had been able to explain for 20 years. It is called the CMB Cold Spot, and it connects to an idea that changes the scale of everything. The cosmic microwave background is not perfectly uniform. It carries tiny fluctuations, temperature variations on the order of 1 part in 100,000, encoding the seeds of every galaxy and cluster we see today. These fluctuations have been mapped with remarkable precision by the WMAP and Planck satellites. Their pattern matches the predictions of inflation beautifully, almost. In the southern sky in the direction of the constellation Eridanus, there is a region of the microwave background that is colder than it should be. Not slightly colder, significantly colder, around 70 microkelvin below average, spread across an angular patch roughly 5 degrees wide. In CMB terms, that is enormous. It is the single largest anomaly in the oldest map of the universe we possess. It was first flagged in 2004. In the 2 decades since, it has been the target of intense investigation. The first explanation was a supervoid, a massive region of below-average matter density along the line of sight. In 2021, researchers using dark energy survey data confirmed the existence of the Eridanus supervoid, roughly 1.8 billion light-years across and centered about 2 billion light-years from Earth. For a moment, it looked like a resolution. It was not. The supervoid, even confirmed at greater than 5 sigma significance, can only account for roughly 10 to 20% of the observed temperature drop. The integrated Sachs-Wolf effect from a void that size and depth simply is not strong enough to produce the full cold spot signal within the standard Lambda-CDM framework. The cold spot remained larger than any supervoid in the model could explain. The second explanation was statistical noise, a rare but possible fluctuation that needed no new physics. That was technically defensible. It was also unsatisfying because it amounted to arguing that the anomaly was not interesting enough to investigate. And then there is the third explanation, the one that circulated in conversations more freely than it appeared in published papers, a bubble collision imprint. To understand what that means, we need to talk about the most successful theory of the early universe and what it demands whether we want it or not. Inflation is the idea that in the first fraction of a second after the Big Bang, a span of time so short that writing it as a decimal would require more than 30 zeros before you reach the first non-zero digit, the universe expanded exponentially. Not fast, exponential, a region of space smaller than a proton ballooned to macroscopic size in an instant. This sounds absurd, but inflation solves three deep problems in cosmology that have no other clean solution. It explains why the universe looks the same temperature in every direction, even though regions on opposite sides of the observable cosmos should never have had time to communicate with each other. It explains why space is geometrically flat on the largest scales. And it explains the specific pattern of tiny fluctuations imprinted on the cosmic microwave background, the very fluctuations that seeded every galaxy and structure we see today. Every precision measurement of the CMB is consistent with inflation. It is not a fringe idea. It is the leading framework for the universe's earliest moments. The problem is what it implies. Inflation is driven by something called the inflaton field, a field carrying an unusual form of energy that causes space itself to expand exponentially. Quantum mechanics, the most precisely tested theory in the history of science, says the decay of this field is not deterministic, it is probabilistic. In some regions, the field decays quickly and inflation ends, producing a universe like ours. In other regions, the field keeps going, and those still inflating regions produce new volume faster than the decaying regions can fill. The result is that inflation, once it begins, never fully stops. It is eternal. It continues to spawn fresh pockets of non-inflating space indefinitely. Each pocket is a bubble. Each bubble is causally disconnected from the others. Each bubble carries slightly different physical constants depending on the quantum state of the inflaton field at the moment of its decay. Our universe is one of those bubbles, and the mathematics of eternal inflation says there are others, not as a possibility, as a necessity. This framework was first formalized by the physicist André Linde in 1983, later developed alongside Alan Guth, who had originally proposed inflation, and Alexander Vilenkin. Together they built the mathematics of bubble nucleation, bubble expansion, and bubble collision. They calculated what a low-energy bubble collision at the edge of our observable region would look like in our data. They predicted a roughly circular anomaly in the cosmic microwave background, with a specific temperature profile. Those predictions were laid out in the 1990s. Nobody in the observational community paid serious attention. Then the cold spot showed up in the data. It had roughly the shape and roughly the position the collision models had anticipated. In 2012, physicists Hiranya Peiris, Matthew Johnson, Anthony Aguirre, and Max Wainwright built a simulated multiverse with two bubbles to study what an observer would see after a collision. They concluded it would appear as a disk on the CMB with a distinctive temperature profile. The resemblance to the cold spot was never exact enough to confirm the hypothesis. It was also never far enough off to conclusively rule it out. Now stop and sit with that for a second. The most precisely tested framework for the early universe, when you follow its logic honestly using the most precisely tested framework for the behavior of matter, leads you inevitably to the conclusion that other universes exist. The mathematics does not give you a way out. If you accept inflation, and the evidence strongly supports it, and you accept quantum mechanics, which is essentially non-negotiable, then eternal inflation follows automatically. And eternal inflation means bubble universes, and bubble universes can collide, and collisions can leave marks. And we have a mark in the CMB that has gone unexplained for 20 years, sitting in precisely the kind of pattern the theory predicted before the observation was ever made. Einstein did not believe in the multiverse. He spent the last decades of his life chasing a unified theory of everything, a single elegant set of equations describing all of physical reality at once. The idea that reality might be fundamentally plural would have been philosophically repugnant to him, and yet the equations he wrote down left a door open. His general theory of relativity, expressed as a set of 10 field equations linking the geometry of spacetime to the distribution of mass and energy, allows solutions that describe more than one connected region of space. Solutions where the geometry of space can be multiply connected. One class of these solutions involves what are called domain walls, surfaces in space where a field transitions from one stable energy state to another. If two bubble universes settled into different energy ground states, the boundary between them would be a domain wall. That wall would carry energy. It would curve spacetime. It would bend light in a particular way smoothly across an extended surface, producing a lensing profile flatter and more spread out than any concentrated mass could generate. Einstein did not predict this would happen, but his equations permit it. He left the door open in the mathematics. Whether anything has walked through it is the question the next decade of observation may finally answer. Here is what I want you to take away from all of this. We are living through a moment in cosmology that does not come along often. The Standard Model, the single most successful scientific framework ever constructed for describing the structure of reality, is showing stress fractures from at least 3 independent directions. Galaxies that are too mature, an expansion rate that contradicts itself, a cold spot that refuses to be explained by anything inside the model. None of these anomalies individually proves that something beyond our universe is pressing inward, but taken together they form a pattern. And patterns in independent data sets pointing in the same direction have historically been the first sign that something real is waiting to be found. The Vera Rubin Observatory has just begun its 10-year legacy survey of space and time in Chile, imaging tens of billions of galaxies with enough precision to map weak gravitational lensing across the full sky at a level of detail no previous survey has approached. The Euclid Space Telescope, launched by the European Space Agency in July 2023, is currently mapping the three-dimensional distribution of galaxies across roughly a third of the sky, with its first cosmology data release planned for late 2026. Webb itself continues to observe, each cycle pushing deeper, sharper, and further into the infrared than any instrument before it. Within this decade, we will know whether these cracks widen into something that forces us to redraw the boundaries of what exists, or whether the standard model absorbs them and holds. Either outcome would be extraordinary. The instruments are ready. The question is whether the universe will answer. What we thought we were mapping, the complete self-contained universe from edge to edge, may turn out to be something closer to a room. And somewhere in the data, faint and precise and geometrically strange, we may have already found the outline of a wall. If this is the kind of space science you want explained clearly and honestly, hit subscribe and turn on notifications because there are more stories like this coming, and they only get stranger from here. Drop a comment and tell me which part of this story stopped you in your tracks, because it genuinely helps me figure out which stories to cover next. And if you know someone who needs to hear this, share it with them because this story deserves more than the silence it is getting.